you saw my message, but I was having issues with my audio, and while I was still here, I couldn't speak and let you know that I was marked that I was here. So I think you marked me absent.
Okay, so I'll mark you present in a couple of minutes. Just give me a second. Let me
Okay.
see. And
Yeah, for sure.
okay. So last time we were discussing about the concentrations, right? So today we'll be solving some problems, more problems on concentrations. Just give me a second. And I'm going to copy paste some problems, and then you need to find what is the concentration, and we can go from there, right? Okay, so we did the method of dilution. So I'm going to copy paste this problem. Let me see. Oh, it works. Yeah, by the way, guys, before I proceed further, you remember last time Abraham mentioned something about the exam? Remember that? All of you were there?
I was.
Yeah. So basically, Abraham mentioned at the end of the lecture that there were 3 questions which were carried forward from this chapter into the previous exam. So what I'm going to do, those who got those answers wrong, they will get the points for that, because those questions were supposed to be from exam 2. Somehow they got into exam 1 while we were transferring the Blackboard shells into the Canvas. So good for you that you're going to get the points if you got them wrong. So you will see in some cases, you're going to see your scores going up. And now you know why is that. So you should thank Abram on that, right? Okay. So how about solving this problem? So you are given nitric acid, and we know it is a powerful corrosive agent. In fact, it's quite an acid, I will tell you that, but not as strong as sulfuric acid, right? But if you mix nitric acid with hydrochloric acid, do you know what it forms? There is a mixture called aqua regia. And this mixture, which is 1 nitric acid and 3 HCl, that mixture, 1:3 ratio of nitric and hydrochloric acid, they can dissolve gold in a blink of a second. Imagine that, right? So nitric acid, you are given that. You are given the molarity of nitric acid and how much stock solution. That means you are given the molarity of stock solution, which is 16 molar solution. And you need to prepare 0.5 molar 8-liter solution. How would you do that? Anyone? Any idea about that? Guys, can you hear me?
Yes, we can hear you.
Okay, because I was like, it's a new system, so I was thinking that whether you guys are here or not. Okay. So what do you guys think about this problem? So have you guys heard about the formula M1 V1 equals to M2 V2? Have you guys heard about that formula before? How many of you have heard
Yes.
that? You have heard about that formula, right? Okay. So let me go back here. So while we were discussing, where is that one? Yeah. So we are here. So while we were discussing about the molarity, which is right on slide number 41, as you can see, molarity is moles of solute divided by the volume of solution. Do you guys agree on that? So moles of solute divided by the volume of solution. Now, if I multiply molarity with the volume of solution, would I get the moles of solute? I would get that one, right? Now, keep that in mind and think about this problem now. Why did I write M1 V1 equals to M2 V2? Now think about it. Let me first draw the flask, which you might have used in your Gen Chem 1. Many of you would have done that. So let me take the volumetric flask. Suppose this flask is for 1 liter. The upper mark is 1 liter mark. In this flask, suppose I have 16 molar nitric acid. Now, for example, if I take 100 ml of this nitric acid, can you tell me how many moles do I have in 100 ml? I'm taking 100 ml of 16 molar nitric acid. That means 1 liter has 16 moles. That's what it means. Now I'm taking 100 ml. Very good, Roberto. You are right, right? So when I take 100 ml, that means I am taking 1.6 moles of nitric acid. Now, how did I reach to that conclusion? Let me show you that one. Molarity equals to moles of solute divided by 1 liter solution. That was the molarity. Now, think about it. I'm given 16 molar solution, right? Okay. On this side, suppose I don't know the moles of solute that I have in 100 ml. So can I express my 100 ml as 0.1 liter? I can do that, right? All of you agree with that so far? Okay, so I will rewrite this equation one more time. So 16 molar, that would be equals to moles of solute divided by 0.1, but I can write 0.1 as this one, right? Because after all, 0.1 multiplied by 1 does not change anything, right? So in terms of definition, I'm still having 1 liter in the denominator, which is exactly the definition of molarity. It's moles of solute per 1 liter. So that's, so far I'm fine. So I can simply write my 16 molar. I can expand the units for molar. That's going to be 16 moles per liter. I can do that, right? Okay, now that would be 0.1, 1 liter. Essentially, I can rewrite it as moles of solute. That is going to be 1.6 because you multiply 0.1 with 16 moles. That's how you got the moles of solute in 100 ml, not in 1 liter, in 100 ml. All of you agree that so far? So first of all, I'm going to show you in terms of concept, and then we'll be using this formula. Okay, now let me go back to the flask that we had. See guys, I'm bad at drawing. So this has 16 molar solution, and out of 16 molar, I took 100 ml. Now suppose if I took this 100 ml and I put it in another flask, which is also 1 liter flask, and I take 100 ml, which is now here at the bottom of the flask, and then I add water to this. So I'm adding 900 ml of water so that my total volume in my volumetric flask is now 1 liter. Can you tell me how many moles do I have in this flask? How many moles of nitric acid do I have in this flask? Before you answer that question, this one had 1.6 moles. You just calculated that. 100 ml contained 1.6 moles. And I'm adding that over here. So how many moles do I have in flask number 2? Very good, Roberto. You are right. So I'm not changing the number of moles in my flask number 2. So I'll just say flask A and flask B. See, number of moles did not change here. But now the same number of moles which were contained in 100 ml now are in 1 liter. So now when I calculate the molarity, that's going to be moles of solute divided by 1 liter of solution. So that's going to be 1.6 moles divided by 1 liter solution. So now you are looking at the molarity, which is 1.6 molar solution. This method is called dilution method. And this solution, we call it stock solution. So stock solution is always concentrated solution. And then you can prepare as many dilute solution as you want, as long as you have the stock solution with you. So I can prepare 1.6 molar solution of nitric acid right from my stock solution, or I can prepare, in that sense, I can prepare any molarity which is less than 16 molar using my stock solution, right? Now, this method, the one which I showed you, that was based on the concept. You first converted your molarity into number of moles, and now you know that the number of moles in your solution over here in 100 ml and in 1 liter was the same, right? So now let me convert that into the equation. M1 V1. What does it mean? It gives you the number of moles in 100 ml. Let's do this one more time. Let me see what we have here in the chat. Okay, so we started with 16 molar solution and we took 100 ml of that. Now, if you are converting your molarity into number of moles, then you need to convert your milliliters into liters. But if you are using the formula M1, V1, M2, V2, you don't need to do that. And you will just see in next couple of minutes why you don't need to do that. So this is going to give you 16 molar multiplied by 100 ml will give you the number of moles that we just found, 1.6 moles. But now when I made 1 liter solution out of it, that was another solution. That was M2V2, right? Now look at the number of moles in that one. We just calculated using the long method, it was 1.6 molar solution. And we just use 1000 ml, which is 1 liter, 1.6 moles. See, now the number of moles is the same on both the sides. So If this was X, if this was Y, and if this was Z, can I say if X equals to Z, Y equals to Z, can I say X equals to Y? I can do that, right? In the same way, now I'm getting to the equation M1 V1, which was X, that's equals to M2 V2. Because when you multiply volume with molarity, essentially you are getting the number of moles. Now getting back to the real problem that we started with. Let me copy this problem one more time. Now can you find me the molarity using this equation? Anyone so far? Okay, so here you need to find the volume. You are given the molarity. So M1 is given to you 16 molar. M2, V1, we don't know how much stock solution we should be using. So that's what we need to find. M2, which is your resulting solution, the dilute solution, that is 8 liters. And sorry, that one is the volume. Let me. And M2 is 0.05 molar. So if you use this equation, M1 V1 M2 V2, so you are given 16 molar multiplied by V1, that's going to be 0.05 molar multiplied by, we are given V2, which is 8.00 liters. So V1 is going to be 0.05 molar multiplied by 8 liters divided by 16 molar. So you can cancel out molar from the numerator and the denominator. And what you get is 250 milliliters or 0.25 liters. So far, so good. Any doubts so far on that one? Are we on the same page? Okay. So how about solving one more problem? Let's see if you guys can do this one. This is quite an interesting problem. A real world problem. So you are given hydrochloric acid that you can buy from the stores, and you are given the mass percent of hydrochloric acid. That's 32% by weight. You are also given density of hydrochloric acid, and you need to convert this into molarity. How would you do that? Think about it and let me know. I'll give you 2 minutes to think about it.
Professor, hi. I don't know if you got my message. I came in a little bit late because I was having connection issues.
Yeah, I saw that message. Oh, yeah. So I'll put the attendance after we are done.
Okay, perfect. Thank you so much.
Okay, guys. So I'll give you 2 minutes. Think about this problem. Let me give you a hint. Mass percent. That is equals to mass of solute divided by mass of solution multiplied by 100. So how would you approach this problem? And I'll also give you molarity because that's what you need to find. Moles of solute divided by 1 liter solution. That's going to be your molarity. Now you need to use these two equations to get to the answer. Let me give you one more hint over here. Assume that you are given 100 grams of hydrochloric acid solution. So if you are given 100 grams, how many grams is actually hydrochloric acid in that? That would be your first hint. Then the second hint is molarity includes moles, not weight. The first one will give you the weight of your solute and the weight of your solution. How would you convert the weight of solute into the moles? Number one. How would you convert your mass of solution into the volume of solution? Because that's what you need in the numerator and the denominator for the molarity. So while you are doing it, I will just go back to the attendance and look into the chat and work on that. So I'll give you 2 minutes to do that.
Professor, I just had a quick question.
Yes, go ahead.
I was wondering if you were going to post like a new module with like all the different chapters.
New module with the different chapters.
Yeah,
Can you?
like you did with chapter 11, 12, 13. I thought you were just gonna post like another module with like, the chapter that we're doing now in class and then the other chapters.
So it's not there?
No, on my end, I don't see it.
Yeah, it's not posted on Canvas.
So even this chapter is not posted on the Canvas? Let me check because shouldn't be happening like that. It stops at chapter 13. So up till chapter 13, it is there, right? Okay, yeah, I get that one. So I will open it right now. First, let me look into.
Professor,
Yes.
remember to extend the quiz for
Mhm. Yeah, yeah,
chapter 13.
yeah, yeah, yeah. Once we complete that, I'm going to do that today.
All right, perfect. Thank you.
Mm-hmm. So I'm going to move the due date for that practice quiz until next week. So don't worry about that, Kaylin. Mm-hmm. So where are we so far in the problem? Let's see what we got here. So step number 1, if you are given 32%, in this case, I did not give you the mass. So I will assume that you are given 100 grams of HCl solution. That way, now the mass of HCl in 100 grams is 32 grams. And I got that value from 32% because what exactly is 32%? It's the mass of solute divided by the mass of solution. If the mass of solution is 100 grams, that means the mass of solute is 32 grams. So you got that weight from there. Now, I need to convert my mass of HCl into moles of HCl. What is the molar mass of HCl, guys? Anyone? I need a conversion factor here. The molar mass of HCl, let's see, 36.46, that's right. So 36.46 grams is the mass of hydrochloric acid, that's per mole. So can you tell me how many moles are we looking at? 0.8779. Okay, so I will say 0.88 moles because we'll keep it at 2 sig figs. So we have 0.88 moles of HCl. So we found that one, right? Now, the next thing is we need to find our volume, the volume of solution. But then instead of volume, we are given 100 grams, right? Because that's where we assumed. So how do I convert my volume, the mass into volume? So I will say volume of solution. How do I do that? I'll just show you over here. So we are given 100 grams of solution. And when you look at the information that's been provided to us, we have been given density, which is 1.1593. That one is in grams per milliliter. So I'll just write here 1.1593 grams per milliliter. Is this right conversion factor? The way I have written, is this correct? Can I simply?
No, should be the reciprocal.
Exactly. It should be the other way around because you can use your density as a conversion factor. So that one will give you two conversion factors. One is going to be 1 milliliter divided by 1.1593 grams. And the second one will be 1.1593 grams divided by 1 milliliter. So if you were given those two, which one would you use? Your final answer should be in milliliters. So milliliters should be in the numerator. So the way I have written my conversion factor is wrong. My weight should be in the denominator. So 1.1593 grams should be in the denominator and 1 mil should be in the numerator. So how much am I looking at in terms of volume? And just write down in the chat box so I know that. How much volume are we looking at? .86.26 milliliters. All of you got that same answer, 86.26. Good. Now the next thing is I got the moles, I got the volume, right? So now I'm going to plug it in the molarity equation. So molarity equals to moles of solute, and the one that we found was 0.88. So I'm going to write 0.88 moles divided by, here we are given volume in milliliters. We want volume in liters because molarity is moles per liter, right? So the volume in liters is going to be 0.08626 liters. Can you give me this answer now? 10.2, very good, or 10 molar. So now you can use the density as the conversion factor. You can use the mass percent to get to the molarity, right? So are we guys comfortable with the problems like these before I go to the next topic? Or is there any doubt?
Anyway, we can do one more.
You guys want to do one more problem on that? Okay, so let's do one more problem then. Okay. So how would you solve this one? These are all practical problems. Think about that. You are given moles. Anyone with the answer? Good, very good. So 0.05 molar, that's a correct one. Very good. Okay. See, now you guys are doing so great. That's the answer. So molarity is moles per liter. So you are given 0.01 moles of sucrose divided by 200 milliliters. So we need to convert our 200 milliliters into liters first, right? So that's going to be 0.2 liters. Now, when you look at the units, you already got your answer in moles per liter. And that one will be 0.05 molar. All of us on the same page so far on this? Okay. So the next part we're going to discuss today is about colligative properties. Now, what exactly is colligative property? Anyone? Any idea what are those properties? Any guess? I believe this was in the videos as well, right? So the colligative properties are the one which depend on the quantity, not the type of solute that we are dealing with. So what do we mean by that? Suppose you have a solution containing 0.1 moles of sodium chloride, and you have 1 liter solution. That means you are looking at 0.1 molar. And you have another solution. This one, instead of containing 0.1 moles, this one is 0.2 moles. And this one contains glucose and 1 liter. Now, when you look at the boiling point of these two solutions, one containing 0.1 moles of NaCl, the second containing 0.2 moles of glucose, you'll be surprised. The boiling point of these two solutions will be the same. The vapor pressure, that means the pressure exerted by the solution onto the atmosphere, is also going to be the same for these two solutions, right? In the same way, when you look at the freezing point, that means the point at which your solution will freeze to the solid state, that will also be the same. And when you look at the osmotic pressure, we are going to discuss about that, but then osmotic pressure is also going to be the same. But then it is kind of strange, right? We are dealing with sodium chloride in one solution. In a second solution, we are dealing with a glucose. So looks like that the nature of solution is not affecting. Can you tell me what is affecting here? If the volume is same, what am I changing here? Anyone? Guys, can you hear me?
Yes, Professor, we can hear you.
Yes, we
Yes.
can hear you.
Okay. So what exactly I'm changing? See, I'm changing the number of moles. In one case, I have sodium chloride, which is 0.1 moles. In the second case, I have glucose, which is 0.2 moles. Now, when I think about 0.1 moles and 0.2 moles, right, I'm increasing the number of moles, right? I'm increasing the number of moles of sodium, from NaCl to glucose. I'm changing the number of moles. But then, is it what exactly is happening? No. If I have 0.1 moles of NaCl, look at how many particles do we have. So sodium chloride, you put it in water, it's going to split into sodium ions and the chloride ions. But then how many sodium ions do we have? Well, 0.1 mole of sodium chloride will split into 0.1 mole of sodium and 0.1 mole of the chloride ions, right? On the same side, when we look at glucose, does glucose split into ions? Answer is no. It's a molecular solid. It will not split into ions. It's not going to dissociate into ions. So 0.2 moles of glucose will stay as 0.2 moles of glucose. That's not going to change. But see what happens over here. The total number of particles that we have in the solution for sodium chloride is now 0.2. Now this number and this number is the same. So what exactly are the colligative properties? So these are the properties which depend on the number of particles in a given solution, not the identity of your solution. So on the left side, yes, you are dealing with a strong electrolyte. On the right side, you are actually dealing with a non-electrolyte, two completely different type of solutions. Yet the colligative properties for both of these solutions are the same. So what are those properties? I'm going to write it down for you. So the first one is vapor pressure. What is vapor pressure? It's the pressure exerted by your solution onto the atmosphere, right? That's the vapor pressure. The second property which is connected to the vapor pressure is your boiling point. So boiling point is also a colligative property, right? But now think about it. When we add a solute in the solvent, something happens to the solvent. It is not the pure solvent anymore. So there will be change in boiling point. See, for example, if you have water, it boils at 100 degrees centigrade. Now, when you add a solute in the solvent, pure solvent, you make a solution, the boiling point will increase. Now, there is a reason for that. I'm going to explain you that. So, boiling point elevation is directly connected to the colligative properties. The third one is also related to the vapor pressure and the intermolecular forces of attraction. What is that? It's a melting point or freezing point. But then what happens to the freezing point when you add a solute in the pure solvent? The freezing point goes down. So there is a depression in freezing point. And the fourth property is osmotic pressure. Now, let's first look at the vapor pressure. What happens to vapor pressure when you put a solute in the solvent? You will generate a solution, but then the vapor pressure of solution, how does it connect with the vapor pressure of solvent? How is it related to that? Vapor pressure will always be lower for the solution than for the pure solvent. Now, there is a reason for that. This is the pure solvent. Suppose this is water. Now, at any given time, at a room temperature, some water molecules are going out and some water molecules are coming in. So there is an equilibrium, right? That's what is happening. And the vapor pressure is basically the pressure exerted by these water molecules onto the outer atmospheric gases, right? That's the vapor pressure. Now imagine if I put a solute in this one, and suppose that solute is sodium chloride. I'm just putting it at the dots. Now my water molecules, the ones that were easily moving out of the solution, now they are bounded to water. So now we don't have enough water molecules going out into the atmosphere. So the vapor pressure is now less compared to the pure solvent. We have less water molecules going out and exerting that pressure. So the vapor pressure decreases. Now, when vapor pressure decreases, that means the water molecules want to stay inside the liquid phase because of those ions. Say, for example, here we are talking of NaCl. Now, water molecules are bound to NaCl. They don't want to leave the water bulk. What happens? The boiling point will increase. It will be difficult for these water molecules to get away from those ions because the ion dipole interaction is a strong interaction. So it will be hard. It will require more energy to dislodge those ions and get them into the vapor phase. So the boiling point will also increase. Vapor pressure will decrease. Boiling point will increase. Now, the similar thing will happen when you have glucose. So you have water, and if you put glucose in that, I'll put glucose in blue so that you can see. Now, in this case, what is exactly happening? The water molecules, just like NaCl, is also surrounding the glucose molecule. But then the nature of interaction is different. Here, the nature of interaction is dipole-dipole interaction. In the previous case, the nature of interaction was ion dipole interaction. Now, as I mentioned, it depends on the number of species that are involved in the solution. So as long as you have the same number of species on the side of NaCl and on the side of glucose, the vapor pressure will be the same for these two solutions. But then that will be always lower than the pure solvent. Pure solvent will always have highest vapor pressure. Keep in mind, I will repeat one more time. Pure solvent will always have higher vapor pressure than the solution. Solution will have always lower vapor pressure. And now you know why is that? Because water molecules or the solvent molecules are tied to the solute. They are not as free as they were before. So it's difficult for us to dislodge those water molecules into the vapor phase, right? Okay, so that is basically the theory behind it, right? But when I say the water molecules, how many water molecules are we looking at? The ones which are going into the vapor phase. Now, let me show you one diagram. This is taken directly from your book, so it's going to be quite helpful for you guys to visualize. Let me paste it here. This is taken directly from your book. So as you can see, we have pure solvent. The moment I add solute, we have less number of solvent molecules getting into the vapor phase. And you can see the vapor pressure is now less compared to the pure solvent. Now, this is just a visual representation. Now, is there any equation which governs the vapor pressure? Answer is yes. Just give me a second. Now, that equation is Raoult's law. How many of you know what Raoult's law is? Anyone? I believe that was there in your video, right? So let me put it here. Anyone with the Raoult's law? Have you guys heard about this? Okay, can you tell me what that is? Now, suppose you have a solute which is dissolved. Okay, let me see. It is like vapor pressure. Yes, yes, you are right, Tamar. It is like vapor pressure. So, you see, yes, we also use the mole fractions over here. No, we are going to do it now. Okay, so if you are looking at the vapor pressure of your solution, so this is the vapor pressure of solution. Now we know that the vapor pressure is directly connected to the boiling point, right? We have seen that before. When we were discussing about the phase diagrams, we saw that one. So the pressure, vapor pressure of solution equals to the mole fraction of your components that are involved in your solution, number one, right? Now, when I say mole fraction, right? So this is going to be the mole fraction of your solution, solvent, multiplied by the pressure of the pure solvent, vapor pressure of the pure solvent. And that one should be multiplied, added to the mole fraction of the second component. So I'm going to add mole fraction of solute multiplied by what should I multiply that with? What do you guys think? You've done that, right? In the video, I saw that most of you have done the videos. This was discussed in the videos. Anyone? Guys, I'm waiting.
What did you ask?
I'm asking whether this equation is right or not on the Raoult's law. So let me ask you this way, because I've seen that most of you have done the videos. So let's start from there.
Professor, I saw on the slides that it's just the pressure of the solution times the mole fraction of solvent and the pressure of the pure solvent. So that added mole fraction is not part of it.
And where would we need to add the vapor pressure and for the pure solvent? Where will that come into picture? because you are going to use a similar equation. So you are right. This is the Raoult's law. But then, what is exactly that one? Do we need that? How many of you think we need that? Let me see. Maybe not. Okay. Someone said maybe not. Okay. So for those who think we need to use the mole fraction of solute differently than that, why you think that? And for those who think we don't need to use them, why is that? So for now, we don't need to use that. But then when would we require to use that? To find the concentration of solute. Okay, I would think about that. Okay. Okay, now here's the thing. When you have two liquids which are making the solution, liquid 1 and liquid 2, both have their own vapor pressure. Am I right on that? Because liquids will always have their own vapor pressure. So liquid A has its own vapor pressure. The pure liquid A will have its own vapor pressure. And then the pure liquid will have its own vapor pressure, right? In that case, you will need to use the equation, which is going to be the modified equation. And that's going to be that. This is when you have liquid solution. This is when you're going to use that equation. But then if you have a solid liquid solution, just like you dissolve NaCl in water, sodium chloride does not have the vapor pressure because it is in a solid form. If you dissolve glucose in water, you do not have the vapor pressure of your glucose because glucose is solid. In that case, you do not use the next part of your equation, which is the mole fraction of solute and the partial pressure of the pure solute. You don't need to use that. You only use the first part of it. Make sense? Now let me draw this in a different form so that you will understand that. You have pure solvent A. I'll just say as A. The molecules are going in and they are coming back. There's an equilibrium. And I'll say 4 of them are going in, 4 of them are coming in. And you have another solvent or probably solute, which is B. In this case, 2 of them are going in, 2 of them are coming out. So this is A and B. Now, if I take small amount of B and I put it in A, what will happen in that case? I'm going to get a solution of B in A. A is basically your solvent. So molecules of A are going in and coming back. Then also now you have interference from your B as well, because you have B over here as well. So B is also in and going back. But now if you are dealing with a miscible liquid, this ratio of going in and coming out will change. And that ratio will depend on the equation partial pressure of solution. That's going to be the mole fraction of A multiplied by the partial pressure of A, pure A, plus mole fraction of B multiplied by partial pressure of the pure B. That will be your modified equation. But then this equation is valid only if you have A and B, which are liquid in form, and they are completely miscible, right? If they are miscible, that means they are interacting with one another. If they're interacting with one another, that means it will not let all 4 molecules go out, and A will make sure that 2 molecules of B do not go out that fast. So it's going to affect each other. And it's also going to affect how much A is going out in atmosphere and how much B is going out in the atmosphere. And that will be governed by this equation. So depending upon what kind of solution you are dealing, you have to be careful about that. Okay. Now let's solve a problem. So first of all, before I go to the problem, are we on the same page on this? Do you understand the concept?
Professor, yes, I understand the concept, but I have a question about it. Because you mentioned that it was in the video. Uh, I don't remember seeing it in the video. Like, I think this is the first time that I'm seeing this.
Are you sure it was not in the video?
Yeah, and I also like kind of like skimmed through it just now, like to see if it was just me misremembering, but I don't see any portion that like about Rawls law. There is a portion about like vapor pressure, but but that equation is not included in that portion.
So the modified equation is not there, or
No, I just don't
Rawls law is
remember
not there.
seeing like I think it's the first time that I see his name, so that was like why I was like confused when you were asking about it. I don't know if it's just me or like I skipped through it maybe. But when I first watched the video, I didn't recall it, and I just like kind of rewatched it very quickly, kind of hovering over it, and I don't remember
Okay.
seeing any of that.
Okay, just give me a second. Just give me a second. That is strange. Well. Just trying to see on my end. You are right on that. I'm not sure why it's not there. Well, In that case, now we did it. Okay, so now you know that, right? So it's not there in the videos.
Yeah,
but
I was
now
just wondering because like it was the first one that I had seen. It was like I was confused for a second.
No, it's fine. It's fine. It's good that you told me about that. So probably not everything was there in the video. Okay, not a problem. Okay, but now you know that we did it here. So it's there. Okay, so how about solving a problem on this one? But then so far, are you fine with this one so far?
Oh no, I understand like everything that you have explained, but it was just
Mm-hmm. Because see, the thing is, not everything would be there in the videos. That's why we are having a lecture, right? Otherwise, you could have done the course with the videos. Okay, but then, see, the idea, the concept of video is to prepare you guys before you attend my lecture, right? It's not just to repeat what was there, it's just to build the base, right? Okay, so now you have a problem here. You have to calculate the vapor pressure of solution, and this vapor pressure is by the solution is formed by dissolving 50 grams of glucose in 500 grams of water. Okay, and you are given the vapor pressure of pure water, which is 47.1 torrs at 37 degrees centigrade. How will you approach this problem? Now, before you do that, let me show you how to find the mole fraction. So mole fraction of any component, say for example, component A, that is going to be the mole fraction of A, the number of moles of A divided by the total number of moles in the given mixture. In the same way, mole fraction of B, that's going to be the number of moles of B divided by the total number of moles in a given mixture. So here, we don't need to worry about B, which is the glucose. Why? Because it is solid. We just need to worry about the mole fraction of A, right? Okay, but then to find A, the mole fraction of A, you need to know the moles of A and moles of B as well. Okay, how do you do that? So I'm just going to write moles of glucose, which is, I will say it is A. That's going to be equals to, you are given 50 grams, right? 50.0 grams. What's the molar mass of glucose, guys? Are you guys getting 180.16 grams? Can you find me the moles of A? And then also find me the moles of water, which is B. And you have 500 grams of water. So 500 grams multiplied by 1 mole. Can you tell me what that is? So 27.74, is it for the glucose or is it for water? glucose. Okay, for glucose 0.278, that makes sense. And how about for water? I see 27.74. Is it for water? Okay, so we found the number of moles. Now, what would be the mole fraction of A? Let's look at that one. That's going to be 0.278 moles divided by 0.278 plus 27.74. Can you tell me what that is?
Professor, I have a question.
Yes,
Is it supposed to be glucose as A, or is it supposed to be like water?
you can take any one of them as A. So once you do that, I'm going to show you something interesting here. So first you find for A. Did you guys get that? So you got 0.00992. All of you got that one? 0.00992. All of you got that one? Okay. So you found mole fraction to be 0.00992. This is for glucose, right? Can you tell me what would be the mole fraction of water? In this case, let's put it as XB. Now here, that is going to be 27.74 divided by 0.278 plus 27.74. Can you find me the mole fraction of water? So here, B is water and A is glucose.
Professor,
99.99008.
would the easier way be like subtracting like 1 minus whatever you got is the other?
That's where I'm getting at. That's where I'm getting at. Yeah. So what was the number that you guys got? You see, 0.99008. Okay. Now what you need to remember is mole fraction of A plus mole fraction of B, that will always be 1. So either you find the mole fractions the way we did it individually, or you can simply subtract 1 and then you can subtract 0.00992 1 minus 0.00992 and you will get the answer as 0.99008. So either way you can do it. Now, why did I show you this method? Because in exam, you may not be provided the information like this one. It may not be that straightforward, right? So you need to know these equations so that you can apply them. right? Now, why is mole fraction of A and mole fraction of B equals to 1? Just look at that one. So mole fraction is Na plus Nb, plus mole fraction of B is Nb over Na plus Nb. If you add them together, you are essentially getting Na plus Nb divided by Na plus Nb. That is equals to 1, right? So you can either subtract from 1 and you get the mole fraction of the second one. That's simple. Or you can follow this method. Any method is fine. Now, going back to the problem. Here, we are given the vapor pressure of pure water, right? Which is 47.1 torrs at 37 degrees centigrade. So out of these two mole fractions, which mole fraction should I be using? Should I be using B? Exactly. So in this case, your the vapor pressure of solution, that's going to be XB multiplied by pure B. Can you tell me the answer now? So you just found the mole fraction 0.99008. That's the mole fraction. And you just found the vapor pressure 47.1 torrs. Can you give me this answer now?
46.63.
46.63. Okay, all of you got that answer? Okay. Now, let's make the things a little more interesting. How about instead of using glucose, so I'll just copy the same problem. Instead of using glucose, how about using sodium chloride? So I'll use the same amount of 50 grams, but then this time I'm going to use 50 grams of sodium chloride. How would I approach this problem? You're going to find the mole fraction the way you did it earlier. But is the mole fraction same now, or is it different? What do you guys think? So, first of all, find moles of sodium chloride. Can you find it for me? You have 50.0 grams multiplied by 1 mole divided by. Can you find the number of moles? What's the molar mass of sodium chloride?
.799.
Molar mass of sodium chloride.
Oh, I got the moles. The molar mass is 62 something. One second.
Is it 62 or something else?
6254.
Are you sure?
NaCl, yeah.
All of you got 6254?
Sorry, no, 1 second. 5554.
Okay. 55? Let's see. 58.35. That looks correct. So can you find me the moles of sodium chloride? Let's see what we have. 0.85. That looks close. So grams. So you just found that it's 0.85 because that's what Abram mentioned in his answer. All of you got that answer? $85.5, so 86, so 0.86. Okay, I'll give that. So you got that one. Okay, can you tell me the number of the mole fraction of water now? Now be very careful with this problem. There is a reason why we are doing it. So to calculate the mole fraction of water, you need to know the mole fraction of solute. But then, is it really that it is 0.85 moles of sodium chloride or something else? What do you think?
What was the question, Professor?
The question is it really 0.85 moles of solute particles in the solution or something else?
0.85 moles of Na ions and 0.85 of Cl ions.
Absolutely. So the moles of solute particles,
Double.
that's going to be double. Exactly. So 0.85 multiplied by 2, that's going to be the total number. So how many particles are we looking at? How many moles of those particles are we looking at?
1.7, yeah.
1.7 moles. Okay, and how many moles of sodium water do we have? So you just calculated that in the previous example. You had 27.74 moles. So moles of water is 27.74 moles. Okay, how about now we look at the mole fraction? So mole fraction of A, which is your solute, that's going to be equals to 1.7 divided by 27.74 plus 1.7. Can you tell me that? Find me the mole fraction of B by doing the math as 1 minus mole fraction of A. What is the mole fraction of A? .058. Okay. B, 1 minus 0.058. What is that number? Now, you could have gone directly for the mole fraction of B, but then I want you guys to practice on it. That's why we are doing for mole fraction A, B, and then we'll be using B. So 0.942 is the mole fraction of B. Find the find the vapor pressure of solution. That's going to be mole fraction of B for water multiplied by pure B. And that's going to be 0.942 2 multiplied by 47.1 torrs. Can you give me that answer now? $44.37 torrs. Now you see, seemingly the same weight had different number of particles. And we can see the depression and freezing point. See, in the previous example, we went from 47.1 to 46.63 torrs. Not a big difference. But then the moment we had sodium chloride, we went from 47.1 to 44.37. There was a big difference in the vapor pressure. So when you put sodium chloride in water, that's going to increase the boiling point way more than you put the same mass of glucose in water. Now, just one more point before we disperse today. How many of you have been in North? How many of you have drove your vehicle in ice or snow? Have you guys done that? Anyone?
Driven in snow? Is that what you're asking?
Yeah.
Yeah, once or twice.
Once or twice. Okay. So basically, if you have lived in North, every day morning, when I was in Wisconsin, they used to spray salt in the morning every day on the snow, and within the matter of hours, the snow will be gone. And the reason why they used to do that was because when you add salt on ice or snow, that's going to depress the freezing point, right? So the ice which melts at 0 degree, now it melts at around -6. So you can still have water instead of snow or ice at -6 degrees. And that's the direct application of the colligative properties. So we'll be discussing one more problem on the freezing point and one problem on osmotic pressure before we get to the next chapter on kinetics. I'm going to open that module and we'll be going from there. Let me know if you have any questions.
Yes, Professor, I came a little late today.
And can you identify yourself?
My name is Naina Ramirez.
Okay, let me see. I think I did mark you present. Let me see. Okay, I marked you present.
What about boiling point elevation? Are we also doing that?
I'm sorry, what's that?
We're doing boiling point elevation as well. So as part of the slides.
Yeah,
Okay,
we're going to do that. Yeah. So let me know if you have any other question. Otherwise, see you guys.
Professor, I also came in late.
And you are?
Ana Evi Cazorla.
Okay, I already marked you present.
Thank you, Professor. Have a good one.
Professor, I know you saw my message. I just want to make sure that you mark me present.
Yes, did that already.
Okay, perfect. Thank you so much.
George, I already did that.
No, this is D'Angelo.